Elastic collision in one dimension. If colliding bodies moves along the same straight path before and after the collision, it is said to be one-dimensional collision. In one-dimensional elastic collision, the relative velocity of approach is equal to the relative velocity of separation. The proof: m1 and m2 be the masses of two bodies moving in a path, and u1 be the initial velocity of m1 and u2 be the initial velocity of m2. When the initial velocity of u1 is greater than initial velocity of u2, they collide for a small interval of time. This is the during collision. Then after collision, v1 be the velocity of m1 and v2 be the velocity of m2. This is after collision. These three figures are needed for us in examination. Now let's come for the other proofs. Consider m1 and m2 be the masses of two bodies A and B moving in a straight line with initial velocity u1 and u2 as shown in figure. We have already shown you a figure. Since u1 is greater than u2, that is u1 is greater than u2, they collide for short interval of time and moves with final velocity v1 and v2 respectively. This respectively means the velocity of A and B. Since collision is perfectly elastic, we should know that in perfectly elastic collision, momentum is conserved and kinetic energy is conserved. These two things are to be noted. This momentum is conserved and kinetic energy is conserved. Now what do you understand by momentum is conserved? This is the total linear momentum before collision is equal to the total linear momentum after collision. This means momentum is conserved. Now how to calculate total linear momentum before collision? That is product of mass and initial velocity of body A plus product of mass and initial velocity of body B. This is the total linear momentum before collision. Then after collision, velocity changes to u1 to v1 and u2 to v2, and masses remain constant. Masses are constant but velocities are changeable. So this is the total linear momentum before collision and this is total linear momentum after collision. Taking this m1 in right hand side, in left hand side, we can take m common, and this is this is m1 common. This is u1 minus p1, and this m2 goes this side, gives negative sign, and m2 common, b2, this b2 minus this u1, this is minus sign. Now this is equation first. Now and we know that kinetic energy is conserved. Total initial kinetic energy is equal to total final kinetic. This is u1 is the initial velocity of body A, u2 is the initial velocity of body B, this b1 is the initial final velocity of body A, and this is of body B. This is 1 by 2 mv square. This is the formula of kinetic energy. And again, like in this process, taking this m1 b1 into left hand side, taking m common, this 2 2 2 2 are cut in this way. So yeah, only one this remains, and taking this into this side, this m common, and u square minus v square equal to m2 p square minus u square, like in above process. Now this is the main part of the calculation. We should divide equation first. This equation first by equation, we should divide equation this second by first. Dividing this equation by this equation, we can know the value like this: m u1 v1, here will be the bracket, and dividing m and m are cut, these are cancelled, so and this remains. And now u1 plus v1, this becomes, when this is the formula of a minus b square is equal to a plus b and a minus b, then a minus b को whole square by a minus b is equal to a plus b, a minus b upon a minus b. This and this side remains a plus b. Like in this and this cut, and u plus v1 remains, and similar process for this. Now this is the u1 and this is the u2. Take this into the right hand side. u1 minus u2 is equal to v2 minus then this is the relative velocity of approach and this is the relative velocity of separation. In this way we can know the relative velocity of approach is equal to relative velocity of separation. This is the method to calculate this is the method to prove relative velocity of approach is equal to the relative velocity of separation. Hope you like this.